we're very fortunate in the IQSE to have a number of truly outstanding people. This guy is one of them. Now, I'm a theoretician, basically, who does experiments because that's what must be done. You have to do experiments or you're not a physicist. On the other hand, I don't really know the nonlinear optical physics of the type that Professor Zheltikov knows. I know nonlinear optical physics at the level of Bloomberg or Shin or Steve Harris. But this guy knows something more. He knows a kind of nonlinear optics, which is sometimes called stochastic nonlinear optics, but in general, it has to do with very intense fields becoming filaments in the atmosphere, for example. I had the good fortune to visit him many years ago at the Russian Quantum Center, which he was director of. It's a fantastic experience. We recently wrote a proposal to the DOE in which he was the lead hero, in my opinion, and we got the money. He has been a professor at Moscow State University. That's like saying he's a professor at Harvard and MIT. That's the best place in Russia, bar none. We're very fortunate to have him here. Thank you for being a member of the IQSE.
Thank you very much, Marlon. This is truly generous, truly wonderful introduction. Thank you. So the topic of the talk is extreme events in nonlinear optics. And it will be about how we cannot realize our opportunities unless we know what our limits are. And of course, it goes both ways. So nonlinear optics is important, and it's so where would we even be without nonlinear optics? Because nonlinear optics gives us more bandwidth, so it's a path toward broader bandwidths, shorter pulse widths, higher radiance, and higher field intensities. So in a nutshell, nonlinear optics allows us to work around second law of thermodynamics applied to linear optics. In linear optics, we cannot increase the bandwidth. We cannot achieve shorter pulse width without increasing the bandwidth. And nonlinear optics allows us to achieve all this. So this is the way how we can achieve new frequencies, how we can generate high order harmonics, no bandwidth limits, pulse compression, parametric gain, Kerr lens mod locking. Where would we be without Kerr lens mod locking? So the lasers, femtosecond lasers, would not be there. Optical solitons, attosecond pulses, attosecond physics becomes possible due to nonlinear optics, and the list goes on and on. But nonlinear optics is also about limits. So if you think about this nonlinear optics 101 slides about self-focusing, how a laser beam, as it propagates through a medium, induces a lens, which is exactly what the Kerr lens is here. So it induces this lens, and then it becomes focused due to the lens that this beam itself induces. Now, this is something that enables Kerr lens mod locking. So this is what works to our advantage, allowing us to come up with this femtosecond laser technology that works in many laboratories. But at the same time, it sets a limit the limit for the peak power that you can achieve in a laser beam without losing the connectedness of this beam, without losing eventually the coherence of this beam. Because what happens when my peak power becomes much higher than the critical power, so this is a critical power, peak power, meaning the pulse energy over the pulse width. So when my peak power in my laser pulse becomes much higher than the critical power of self-focusing, what happens to my beam is that it loses its connectedness. It generates multiple filaments. It breaks up into multiple filaments through all those hotspots across the cross-section of the beam, and then it generates those multiple filaments. The results of supercomputer simulations that we've done already some time ago shows exactly how it's happening. And it's really computationally a very complex problem to deal with, because you are losing also the symmetry, the radial symmetry. It's not necessarily radially symmetric. And once you are not radially symmetric, you have to solve this four-dimensional 3D plus one dimensional computational problem, which is typical computation problem. And then you see how those filaments build up, how the beam loses its connectedness. So above this critical power, self-focusing is wonderful. It is needed. Without self-focusing, our femtosecond lasers wouldn't have been there, but it also sets a fundamental limit on the peak power of the laser beam. And above this critical power of self-focusing, our beam loses its coherence. And on its way toward losing its coherence, it generates all those multiple hotspots. And if the peak power is high enough, this is what's happening to your optical elements. So through spatial and temporal instabilities, the beam and pulse, they tend to break up and giving rise to those field hotspots. The intensity is very high in those hotspot, field hotspots. So what happens is that eventually it induces a breakdown. So you are designing your beam line for a high power laser, and then your laser crystals, your mirrors, your lenses, whatever optics you have along this beam line, they're all prone to this laser damage effect, and sooner or later it breaks down. Now the question is, right, of course, I'm mentioning also time domain effects. And in a way, as far as the equations are concerned, the time variable is very similar to the radial coordinate in space. So if we think about optical solitons, they are wonderful because they allow us to propagate ultra-short pulses, and these pulses do not lose their pulse shape. And their pulse envelope. And this is only possible due to nonlinear optics, when the nonlinear phase balances, compensates the dispersion-induced phase. Without nonlinear optics, without nonlinearity, it wouldn't have been possible to compensate for the dispersion phase. Now, in nonlinear optics, it is possible, and then the phase remains plane. So the nonlinear phase shift compensates the dispersion-induced phase shift, and this allows a pulse to propagate without losing its pulse shape, without losing its intensity. So this is what's happening in optical fibers, and of course, this is a very successful field of nonlinear optics. But then again, here, similar to what we have in beam self-focusing, here we have this critical power. For beam self-focusing, we have the critical power of self-focusing. For solitons, we need this peak power because we need this nonlinearity to compensate this dispersion. So we always have this kind of critical peak power. And if our peak power in the laser pulse is much higher than this peak power, then what happens to a soliton is pretty much what happens to a beam. right? So this t variable, t coordinate here, the time coordinate is very similar to the transverse coordinate as far as equations are concerned. Equations are identical in certain approximations. And now what happens here, this is a breathing soliton dynamics, where we have multiple solitons, and they're still coupled to each other because this is a simulation. Everything is wonderful in simulations. You include only the kernel linearity, instantaneous nonlinearity, and only the second order dispersion. And this is where this breathing dynamics shows up. So it's beautiful, it's breathing, so it's periodic in the time domain and also in the spectral domain. But then what usually happens when you include, so this is nonlinear Schrödinger equation, meaning that you include only what you need to preserve this beautiful breathing dynamics, meaning instantaneous nonlinearity and second order dispersion. Now, but if you include high order dispersion, things become less controllable. So this bound soliton state is no longer there. You have this soliton fission effect. The solitons, each soliton is now on its own. It propagates with its own group velocity. And this is how the soliton are no longer coupled to each other. Then they no longer combine to form this bound state dynamics. So this is the limit as far as this breathing soliton dynamics is concerned. And at the same time, this is an opportunity, because by engineering your dispersion and basically your experiment, by designing your experiment in the right way, you can generate much shorter pulses. So this is a technique that has been developed and has been designed for many groups, including our group in the past, as a technique for the generation of very short pulses, sometimes single cycle pulses. And it has been demonstrated experimentally in our experiments together with the group of Andres Baltushka in Vienna, and also in the experiments of our group. In filaments, this is what's happening here, in multiple filaments and in hollow waveguide. So this works experimentally, no question. Now, what usually happens, so this shows how beautiful this breathing soliton dynamics is. Once again, this periodic evolution in the time domain and also in the spectral domain. Of course, they are connected to each other through the Fourier transform. So we have this breathing dynamics. Now, if we include high order dispersion effects, then it's still beautiful as far as I'm concerned, because it gives you, again, if you are doing things right, you can generate ultra short pulses, sub-cycle pulses, again, in theory at least. It's always a question whether you can get those sub-cycle pulses in experiment, but experiments show that, in fact, you can. And now it starts happening here. You start observing all this kind of noisy structure, these stochastic features in the pulse. And this is fundamental. This is inevitable, because this entire soliton breathing dynamics, it starts to build up. The first phase is always modulation and stability. So what happens, the pulse becomes unstable. Right? So you're coming up with your pulse, Gaussian pulse, and then it becomes unstable, so it breaks up into solitons. This is exactly what happens to a laser beam when it breaks up to multiple filaments. So now my question is, can I design it in a meaningful way, or can I avoid my beam breakup or pulse breakup if my intention is to do that? For example, to design this high power, high energy laser beamline for high energy pulses. And it seems like all the tools are there. So usually in real life, of course, it's not that I have just one. So this is my peak power. This is what I'm usually assigning to my pulse as its parameter. The peak power, I divide the energy within my pulse over its pulse width. And this is my peak power, right? And I have this tendency of thinking about my pulse in terms of this parameter. But of course, in reality, I have a distribution. There's always distribution in statistical sense. So with each new pulse, and even sometimes within the pulse, I have fluctuations inevitably. Even if you look at the specs of the most advanced laser systems, there's always some fluctuation parameter. The energy fluctuates, the pulse width fluctuates, the sensor wavelengths fluctuates a little bit. And unless you are paying much attention to that, unless you're really making it difficult and expensive by stabilizing everything, but even then, there's always some distribution, right? Nothing is really it's never its delta function. So what I have here is the probability density function, right? Probability density function. The probability, if I have many pulses, the probability to find a pulse with this peak power. And usually this is where the center, my nominal peak power is usually the center of my distribution. Now, if I want to work below the critical power of self-focusing or pulse breakup, I'm choosing my nominal peak power well below or just below the critical power of self-focusing. Of course, I want this peak power to be as high as possible. So I have this tendency of working close to this threshold. And then, of course, I have this wonderful technology of chopped pulse amplification. CPA technology is designed to solve exactly this problem, right? It helps me to stretch my pulse without losing its spectral bandwidth, without losing the spectral content, in such a way that my peak power, I'm reducing my peak power by stretching the pulse, which allows me to work below, which allows me to avoid allows me to avoid self-focusing, right? And then I will be able, after amplifying the pulse, I should be able to compress it because I haven't lost my bandwidth. So this is more or less the statistical view, the statistical perspective. This is what I have. Now, I still have this probability, of course. I can calculate the probability that things will go wrong, right? So this will be my probability. This is my probability density function. This is my critical power of whatever. Beam breakup, pulse breakup, beam breakup, pulse breakup. So this is my probability that things may go wrong, right? I'm taking this integral of my probability density function to the infinity. So this part here, this area under this curve here, is my probability that things will go wrong. Now, but this is my distribution that I'm assigning to a pulse. Within each pulse, I know that this is my probability distribution. But what if I have many pulses? Right? Many pulses. Because I'm designing my experiment in this way, but then I'm working, then it works nice, it works well one day, the next day, and then in a week, I'm still getting my breakdown. I still have my mirror damaged, right? In a week, I see this picture, right? One morning, one beautiful morning, I see that all my beam line is gone, all my optics is gone. So I have really many pulses, really many pulses. So it goes on and on. And then at a certain point, I will have some probability to have this, what they call in the stock market, black swan, right? Among all those nice white swans, I have one which is black. And it's also beautiful in my mind, but it's still right. So black swan. So the probability, this will be my probability of black swan event within a single pulse. But again, within a single pulse, I don't even call it a black swan. Usually is the probability when I have many events and then some disaster happens, right? Really damaging phenomena. Low probability, but low damage. And remember, this is my probability for a single pulse, and I have multiple pulses, right? Of course, I know all the tools. I know how to do this. I still calculate the same integral, right? Then I subtract this integral from 1, and then take the nth power of this, and this will be my probability of no black swan, right? I have n pulses, n capital pulses, right? So this is my n capital pulses, and I don't want to see this black swan here. So this is my probability of having no black swan probability within a sample of n pulses. Now things become sensitive to this n capital, to the size of the sample, right? So this is my sample size. N capital is the size of my sample size, and this is my probability of having no black swan, right? Now, so I can calculate it, of course, given this simple distribution. If this distribution is simple, of course, I can do this. If not analytically, I can compute things. I can do this, but can I do it something in a more elegant way, right? And in fact, yes, I can. I can do this. I can prove that whatever my distribution is, right, my original distribution is, the limit of this value, which is no black swan probability. Once again, let me call it for the purpose of this talk today, no black swan probability. The limit of this black swan probability, if this x is high enough, and if this n is large enough, so this limit, if it exists at all, it can only exist in the class of 3 possible functions, right? So this limit exists only in the class of 3 possible functions. So remember, this will be not the distribution itself, it will be the cumulative function of the distribution. Cumulative function is, given the distribution, is a probability that this p is less than no larger than p critical. So this will be the cumulative function, the standard way to define the cumulative function in statistics. So it will be the cumulative function. The distribution itself, shown here, will be the derivative of the cumulative function. So whatever distribution I take right here, whatever my statistical distribution is, my limit, if the limit exists, it is reached only within 3 classes of functions. And this statement, and those 3 classes of functions are called Gumbel distribution, Fréchet distribution, and Weibull distribution. And this statement is known as the Fisher-Tippett-Gnedenka theory, right? So upon this linear normalization, the z, if those constants, I can reformulate this. As long as those constants exist, then this theorem works. So I have Fisher, Tippett, Gnedenka. And it started with Tippett. He was, of course, a prominent scientist, a prominent statistician. He graduated from Imperial College in London. And then he studied for his Master of Science in Statistics with Karl Pearson. So this is how he got his knowledge of statistics. So it was in UCL, University College of London. And of course, he worked with Ronald Fisher. And then he was employed by the British Cotton Industry Research Association, and he worked to make cotton threads stronger. So he was thinking about how to make those cotton threads stronger, and he realized while working on this problem that this, of course, the strength, quite intuitive, the strength of a thread is controlled by the strength of its weakest fiber. Right? So, and then he knew, of course, Ronald Fisher, and then Fisher helped him. So this is Fisher, and this is the list of why we know who Fisher is. Sir Ronald Fisher, of course, Fisher information, it opens the list. And then it goes on and on. So he contributed to biology tremendously. He came up with those mathematical foundations of Darwin's selection theory. So he's now Gnedenka, right? So this brings me to Gnedenka, Boris Vladimirovich Gnedenka. Now he was born in Simbirsk, now Ulyanovsk. graduated from Saratov, and when he graduated, I think he was 18 years old. So when he joined the university, he was 15 years old or something. And then he got his PhD from Moscow State University. And as a PhD student, he worked with Andrei Kolmogorov and with Hinchin. And of course, Andrei Kolmogorov was one of the most accomplished mathematicians, scientists ever lived, right? So he, contributed, so he knew how to identify fundamental problems. Then he was professor at Moscow State University. Then he was a correspondent member of the Academy of Sciences of Ukrainian SSR. And this is how he moved to Lvov. Now, this was in 1945. So Lvov just became a part of the Soviet Union right after World War II. So Lvov became a part of Russia, and so he was delegated there. Then he worked in Kiev, then in Berlin, East Berlin, and then he returned to Moscow, and he was professor at MIHMAT, Mechanical Mathematical Department at Moscow State University. And he wrote some beautiful books, and this is how many people.
Did you ever cross paths with him?
No. But of course, what I learned, his books were not my main textbooks because they are more for mathematicians. But for mathematicians, I don't know, Gordon, how popular Gnedenka's book are now these days, but of course I know so it's in the culture of statisticians, used to be the culture of statistical scientists to work from his books. So as far as publications are concerned, so this is one of the Gnedenka's papers, and this is the paper by Fisher and Tippett, exactly starting this entire business of Fisher, Tippett, and Gnedenka theory. So in a nutshell, I put some lines. I'm not going to prove this entire Fisher-Gnedenka theorem, but it all comes from here, from this wonderful product limit representation of or definition even, of the exponential, right? So you have this limit, and the idea is that if you're looking at this, again, for the purpose of my talk, I decided to call it no black swan probability today. The probability of no black swan, that what I'm doing here, right? My whole idea is that I want to find, not to look at the mean, not to look at the mean of this entire probability, because for the mean, I have the central limit theorem. For central limit theorem, I know that whatever my distribution is, when I have many of those swans, or many of those pulses, my mean will be Gaussian distributed, will be normally distributed. This is the central limit theorem. So Fisher-Gnedenka-Tippett theorem, let me put it this way. I think this is more or less accurate. Fisher-Tippett-Gnedenka theorem plays the same role as the central limit theorem, but for the maximum. Right? So I'm interested in what the maximum of all the peak powers of all those pulses in my large sample of pulses is, right? What is the maximum? And so I know that the probability that my maximum is not larger than certain x is given by by one of those three functions, right? Exponential of minus exponential, exponential of minus this, and then I can also kind of revert it. Now, it is proved through this limit. So the idea is that if my threshold, if I'm choosing my threshold, which is high enough, then, so this is identical, of course, I can always write this. I'm multiplying my cumulative function in time. So it will be 1 minus this. So this is, of course, identical. And then I'm choosing this u to be high enough so that this is a constant. And then this term here is simply 1 minus this constant over n, not necessarily constant, maybe x dependent though, and it is x dependent. Tau over n plus some small, right? Some small of 1 over n. And this is exactly where this exponential shows up. And you see that all those exponentials are here, this exponential here. So this is how this exponential here, this exponential here, and this exponential here emerge. And this gives a sense of those distributions. So distributions, once again, are the derivatives of this F1, F2, and F3. And this shows that we have this Gumbel distribution, which is the blue curve. We have the Weibel distribution, which is green, and we have this Fréchet distribution. And interestingly enough, the Fréchet distribution is long tail distribution. So this is exponentially decaying. This one is exponentially decaying curve. But now Fréchet distribution is long tail distribution. And I will get back to this property later because it helps me understand something I need to understand about extreme events, about re-events, about rogue waves in there. Now, stochastic laser field and its statistics. So I need to come up with a model of my pulse, of my laser field, more general. So I'm modeling it as a sum or the superposition of a regular part and noise, right? And then, long story short, my distribution of my pulse, statistical distribution of my envelope will be Rice distribution. And again, this is a deep result. So you always, Rice distribution is a distribution that describes the probability distribution of the magnitude of circularly symmetric bivariate normal variable, right? Bivariate comes from the fact that we always have two components for this envelope, right? We have two independent, in Soviet literature, in Russian literature, they usually called quadratures, right? Quadratures is something that Soviet and Russian physicists and statistical scientists, they like this. So we have two quadratures, two independent Gaussian distributed quantities. And then the magnitude, right? We have this magnitude here, square of rho 1 squared, rho 2 squared, and then the square root of this. So the magnitude of this is always Rice distributed, right? And these models, of course, in radio signals, it's always, we have this generic setting, generic meaning of what the Rice distribution is that we have the signal that is transmitted along the line of sight, LOS, line of sight in communication system, line of sight. And then there will be the scattered signal, right? Reflected from all the buildings, reflected from the atmosphere. So you have this part of the signal. So then your signal will have this Rice distribution, right? With the signal to noise. Now, depending on whether this line of sight signal that propagates in the forward direction, compared to this gives me my signal to noise. This gives me my signal to noise, very convenient. This is an important parameter, also important for my laser pulses. Now, what happens when I have no mean, when it's pure noise makes sense. When it has a pure noise, I have a Rayleigh distribution. Rayleigh distribution, when I have just two Gaussian components, they give me this Rayleigh distribution for the envelope. So Rayleigh, right, my compact closed form analytical result, Rayleigh is zero mean Rice, right? Now, if my signal to noise ratio is high, then my Rice distribution is reduced. So the same distribution right here, it reduces to the Gaussian distribution. Gaussian with of course centered at my peak power S, or more accurately, the envelope rho S, regular envelope. So Gauss, Rayleigh is zero mean Rice, and Gauss is high signal to noise Rice. So from my Rice, I can recover as limiting cases the Rayleigh distribution and the Gauss distribution. So this is the model of my pulse, of my laser pulse. And now here comes nonlinearity. Nonlinearity transforms my statistics, right? So this is my statistics that I'm starting with. This is my statistic of my laser pulse, Rayleigh distribution, but most often it's Gaussian distribution, of course, because I tend to believe that I'm working with nice high signal to noise ratio beams and pulses, and all pulses. The description will be the same. So I have this distribution of my envelope, and then nonlinearity transforms. And then if there's just nonlinearity psi of rho, nonlinearity, like, for example, in the case of the Kerr effect, it will be rho squared, alpha rho squared. So this will give me my typical Kerr effect, third harmonic generation, third order nonlinearity will give me this. And I know this psi or d rho, this derivative here. I need to take the inverse of that. And then I know how to transform my nonlinearity in principle. In principle, I have all the tools. And with this tool, I can continue, I can move on. Again, for polynomial nonlinearity, important class of nonlinearities, which can be written as alpha rho to power n, generally. For n equal to 2, I will have self-phase modulation, cross-phase modulation, self-focusing cover, right? For n equal to 2, I'm describing those important effects: self-phase modulation, cross-phase modulation, self-focusing. So I'm describing, for example, how my Kerr lens mod locking works in my femtosecond laser, or I'm describing my supercontinuum generation when I think about supercontinuum generation in the limits of self-phase modulation. Now, but I can think about n higher than 2, and then it will be perturbative harmonic generation, high order harmonic generation, multiphoton absorption, multiphoton ionization, high order Kerr effect, right? They're all covered by this result, by this expression, by this formula. And I need to go back here and then to do this transformation. This is what I'm doing, and then I will have to take this limit. And if I'm doing all this, right, again, polynomial nonlinearity of this form, and then what I find is that the extreme value statistics is always Gumbelian. So it's this. Gumbelian statistics is these statistics here, right? Exponential of minus exponential. Again, this is my no black swan probability. No black swan probability. And then what happens is that the probability is shown by those solid lines here. Now these dashed lines here show this function here, this one. Now the probability will be, again, it will be the derivative. This is a cumulative function, cumulative distribution function. My probability density function will be the derivative of this. So what happens here, and I'm increasing n, I'm increasing the sample size, I'm increasing the number of pulses, the number of swans, right? Now this curve here, this blue curve here, shows me that as I'm approaching 4, right? So I need to go to x as high as 4 times something, right? In fact, it will be natural logarithm of 10 of 100, whatever it is. As I'm approaching this value, my no black swan probability becomes almost 1. It tends to 1. No black swan. So I have to work here to avoid black swans in my sample size, in my sample of a large sample of swans, or avoid a pulse whose peak power exceeds my limit, right? And this x here is defined exactly as psi or psi naught, and psi naught relates to my limit. So it's not enough to work just below. So the result here is that it's not enough to work just below the threshold of self-focusing, or threshold of pulse breakup into multiple spikes. I need to work below the threshold minus, should be threshold minus this a sub n, because this z here is this linearly renormalized x, where x is my peak power normalized to my threshold. And it's minus this, what is called the location parameter. And this is location parameter. And then this location parameter, it's quite general. For any n, it will be natural logarithm to the power of n over 2. So conveniently enough, n equal to 2, it becomes simply natural logarithm of n. And this is why it shifts the maximum of my distribution And this step here, this step in the cumulative distribution function, it shifts as the natural logarithm of n. So the larger my sample size is, the deeper below the threshold I need to work, or the other way around. If I'm fixing my peak power relative to the threshold, I'm fixing my x, then I know how many pulses my beamline will survive. Again, in statistical sense, I know I can design my beamline this way. Right? I can design my beamline for a certain lifetime. I know what the lifetime of my system is, because it's with the lifetime. If we want to calculate the time, then of course we need to multiply this n by the time between the pulses. If your pulses are megahertz or in gigahertz repetition rate, then of course you are getting millions or even billions of pulses per second. But if you have one pulse per day, of course, then the lifetime will be much longer. And one pulse, one shot per day, even sometimes a couple of pulses per PhD thesis is pretty normal repetition rate for high power laser.
Question there.
Yes.
So can you remind me that which parameter has the mean intensity of the original pulse, the covariant component?
Of the original component, it will be this x. The original component, you mean whatever, I mean the peak power of the input field. It will be this x. It will be this x. Normalized, so it will be normalized. So it is this x. So this is where I'm coming with this. So it means that
am I right in understanding that when you have higher order polynomial nonlinearity, the noise increases?
Right. And this shows up here. This is when you have high order nonlinearity, the contribution, right, of course.
The B parameter, your B parameter
Yeah.
goes up.
Absolutely. When you have a high nonlinearity, you can say it from here, from this derivative. When you have a higher nonlinearity, for example, multiphoton absorption, multiphoton ionization, noise increase, and of course in quantum optics, this has been appreciated. This has been appreciated in all those photon counting business. So there's a culture of quantum optics work showing exactly that, showing that high nonlinearity gives you non-Gaussian. If you start with Gaussian, it becomes non-Gaussian, and it's exactly this. But I'm making one step further. So this is a simply, you see it here. It becomes non-Gaussian, becomes the contribution of noise increases. Here, it hits me here. It hits me on this parameter. It hits me on this N/2, strong dependent.
But the parameter B, I think, is more a measure of noise.
V is exactly the measure of noise. V is
little b, which you have on the next slide.
Yeah. V is rho. Rho is missing here. V is rho over sigma. It's exactly as you said. It's a inverse measure of noise. Rho over sigma. A is my signal to noise ratio because I'm taking my regular part of the pulse, right? Rho sub S is the envelope of the purely regular part, no noise. Sigma characterizes noise through the signal to noise ratio and through normalization of my V parameter. Right? So this is the story. This is the story of polynomial nonlinearity. So for the polynomial nonlinearity, I know everything. Now but I also have this interesting opportunity, which is the exponential nonlinearity. And exponential nonlinearity is important because I have this exponential nonlinearity showing up in modulation instabilities. This is how my noise builds up. This is how the pulse starts to break up into spikes, into solitons. And this is how my beam starts to break up into filaments. It is always seeded by noise. In computation, it's pretty simple. It's pretty clear. Unless you seed your computation with noise, those sidebands will never show up. I mean, of course, in experiments, they are always there because experiments are full of noise. But in computation, you always have to come up with some little model of noise to see those. And then, so it's spatial modulation stabilities, it's modulation stabilities in time domain, once again, beam break up into multiple filaments, pulse break up into solitons. Then it's laser amplification, parametric gain, parametric amplification, stimulated Raman scattering, stimulated Brillouin scattering. All those processes you can find in different regimes, or even as a most generic idea, you will find this exponential nonlinearity of this form, that this raw, this statistical raw, this stochastic, the envelope of a stochastic pulse shows up here in the argument of this exponential, defining my gain. This is pretty typical for all those processes. And then things become even more interesting, because as you're calculating, as you're thinking about this nonlinear transform, the function the probability distribution for this already nonlinear signal becomes the Pareto distribution. The Pareto distribution is interesting. This is a distribution of wealth, this 20-80 distribution, right? 20% of people are doing 80% of work, and 80% of work, we have a tendency of doing 80% of work within 20% of time before the deadline. All those, I mean, this is all the Pareto distribution. And we have this Pareto distribution here. And Pareto distribution is interesting because now here where the Fréchet distribution shows up, right? So it's no longer Gumbelian. Gumbelian describes everything as far as nonlinear optics of polynomial nonlinearity is concerned. But if you have exponential nonlinearity, then it's different. It's Fréchet distribution. Again, related, we have this relation and we have this hierarchy. We have Pareto distribution, which describes the distribution of the signal. But then the extreme value distribution, the limiting distribution, this limit, this no black swan limit, is described by the Fréchet distribution. And Fréchet distribution is different. Fréchet distribution has this heavier tail, heavier compared to the, so this is my Gumbel distribution, and this is my Fréchet distribution. So right here, I start appreciating that my tail here is heavier. And of course, I can quantify it. I have all those parameters to quantify my tail, the tail index kurtosis. I can do that, and of course they are quantified, so they're there. Now here I'm deriving this, and I see that I'm finding the parameters, and I see how it shifts as a function of n, and how it shifts as a function of gamma, and gamma is basically what my gain here is. So gamma quantify my gain. And as I'm increasing this gain, of course, I'm changing the entire picture. Now, so I can have Gumbel distribution, I can have Fréchet distribution. Now, there's also something interesting happening here. As I'm setting my threshold, now I'm asking myself a question. What is the probability to have my large sample size of pulses, large sample of swans, and to have the probability of having exactly 1, 2, 3, 4, 5 pulses whose peak power is higher than what I need, than my threshold, right? Or what is the probability to find 5 black swans among this huge population of swans, right? Exactly 5. And it turns out that, again, due to some very general properties, right? As you're increasing the threshold, then those exceedances over the threshold, they become independent, and they tend to show up at a constant rate, right? And this is where the Poisson distribution shows up. And it does. You can show it mathematically in a mathematically rigorous way, that the probability to find exactly k black swans here in my large population of swans will be Poisson distributed. So this is, I mean, fundamentally, the Poisson distribution always shows up when it's when we have this we have independent events occurring at a constant rate. Now here it's a generalized Poisson distribution, because we tend to think about this tau here as our constant, right? Again, it shows up at a constant rate. Now here in this business of extreme events, this tau, which is the mean of this Poisson distribution, it is the argument. It is the argument of my limiting distributions, right? So it depends on my x, depending again how far above the threshold, or usually how far beyond the threshold, how deeply beyond the threshold I am. I can engineer this, right? And then it will be a function. So it's generalized Poisson distribution. So my mean is not just a constant, but exactly what I have here in my, I can represent all three extreme value distribution through this compact form, right? All three of them. I can write it exponential, right? So those are my distributions. And I can represent all of them, writing exponential, and this will be my exponent. So I can write them an exponential of this exponent, and this exponent, the exponent of my exponential in the extreme value distribution, gives me the mean of the Poisson distribution, which tells me what the probability to find exactly k black swans in my population is. So this is what I call here the Poisson property of my statistics, right? So of course we all know how it looks, the Poisson distribution. But what is important here is that now, by changing my ratio of my peak power to the threshold, I'm changing where exactly I am. And of course, if I want to work below the mean of 1, so if I want to make sure that I don't have more on the average, I don't have more than one extreme event, I don't have more than one black swan in my population of swans here, this gives me a meaningful criterion. And then this gives me a new threshold of everything, right? Of self-focusing, of pulse breakup into multiple filaments. So if my deterministic nonlinear optics, if my threshold is this critical P, such as the critical power of self-focusing or soliton peak power, then in fact, if I have a stochastic pulse, my threshold will be different. My stochastic threshold, the threshold for my stochastic pulse will be P critical, my deterministic threshold, over 1 plus 1 over A natural logarithm of n squared. Right? This will be my denominator. A is my signal to noise ratio, and n is the number of swans in my samples, or the number of pulses. So this tells me that, again, the larger my n is, if I want to design my beamline for a large number, billions of pulses for many hours of work, then I need to choose my P. I need to choose my peak power of laser pulse much lower than the critical power, the deterministic critical power, than the critical power that the deterministic theory of nonlinear optics gives me. So this is one of the key results of my story today. And then from here, of course, so you can plot them all again, depending on what so this is my signal to noise ratio. And this is my deterministic threshold. And of course, the higher my signal to noise ratio is, the more deterministic I am, the more deterministic my beamline is. And then my curve here tends to this, asymptotically tends to this deterministic limit. But then if my A is low enough, then it deviates significantly as a function of natural logarithm. So we come to realize this fact that for any signal for any non-zero A, for any stochastic field, for any non-zero, for any finite, for any non-infinite signal to noise ratio, because deterministic situation will be A equal to infinity. Right? This is when the signal to noise ratio is infinite. Now, for any finite signal to noise ratio, self-focusing will be, so this is a criterion when we can still work with deterministic nonlinear optics. Otherwise, the question of laser damage, the question of whether we are breaking our optics is not a question of whether we can avoid this, but a question of when it is going to happen. Right? So it's no longer a question of if, but a question of when. Again, to put it in more accurately, it's not a question of whether we can avoid self-focusing or pulse breakup, but a question of how we could possibly manage self-focusing or pulse breakup given the length of the size, and the signal to noise ratio. And now, of course, it has projections to nonlinear optics, and nonlinear optics, people like to think about optical analogs of rogue waves, right? And rogue waves are important phenomena observed in fact, of course, in ocean physics, oceanography, in geosciences, it's already more general rogue wave phenomenon. But of course, those extreme events, they correspond to our risks in finances and the insurance business. So it's financial and insurance risk management. Now, biomedical diagnostics, extreme events in epileptic seizures. So this is a typical EEG signal for epileptical seizures. And then how epileptical seizures tend to build up. In EEG, they're trying to see how they could probably detect the early precursors, the early signatures of this ictal phase during the seizure itself, by looking at the EEG signal. Now, this is one of the famous real real ocean wave record for the rogue wave. And in optics, there's this idea that we can observe those rogue wave phenomena in more or less laboratory environment without in a more controllable way, right? So it gives a more controllable fashion of studying all those rogue wave phenomena. And the approach here is pretty much based on identifying what is usually referred to as L-shaped, like letter L, character L-shaped distribution. Now, of course, thinking about the difference between the Gumbel distribution and the Fréchet distribution, you don't have to think about L-shaped distribution all the time. You can come up with this criterion of whether it's Gumbel distribution or Fréchet distribution, because Gumbel distribution is always exponential. So this is where rogue waves are more or less exponentially decaying, but rogue waves are enhanced. They are coming up more often when the distribution is not Gumbelian, but Fréchet distribution. And then you can quantify, you can come up with a quantifier, with a quantitative number, quantitative measure of what your deviation from usual exponential decay distribution. So I have all those conclusions here, but most importantly, I have this map of extreme event statistics in optics, right? So depending on what my nonlinearity is, what my nonlinear process is, whether it's polynomial, whether it's exponential, or whether it's here, to give an example of Weibel distribution, I'm giving simply a uniformly distributed phase, which is more or less multi-mode laser. Multi-mode laser sometimes gives me Gaussian modes, Gaussian result, because I have modes with more or less with different amplitudes, randomly distributed amplitudes, and constant phase. And you can show how multi-mode system always tends to develop to this uniform phase distribution. So I have this map of extreme event statistics in optics, because this is just linear optics. This is nonlinear optics, but this last part is purely linear. Although they can emerge through nonlinear optics in laser cavities. So polynomial distribution. We have psi readout. So this will be our distribution following the transformation due to the nonlinearity. The extreme event statistics is always Gumbelian, and then we can describe our Poissonian mean, because due to the Poissonian property as a universal property of our extreme event statistics, we know what our extreme event Poissonian mean is. So we know what the probability to find extremely k number of black swans in our sample. Now, if we have a polynomial nonlinearity, such as spatial modulation stability, time domain modulation stability, symmetric scattering, symmetric Boolean scattering, laser gain, then it will be Pareto distribution, and will be in our distribution of nonlinear signal, and it will be Fréchet extreme event distribution, and then our Poissonian distribution will have this compact form. And this is where our extreme event statistics becomes non-exponential, becomes heavy-tailed, non-exponential tail. You can quantify them depending on this gamma parameter. And this is where you can expect enhanced log wave phenomena. So they will come more often, and more unexpected. Right. So you will have all those phenomena here. So at this point, I think this is it. This is my story. This is my story for the day.
Where did our referee go? He's right there. I call on him. This is excellent. Thanks very much.
Thank you.
Could I think of your row waves from a mode point of view? So let me put an infinite number of, let me put some number of modes. Let me write the equations, including the Langevin noise source. And now I ask, what's the probability that the mode evolution will go above a certain line? Will that make contact with what you're doing?
Yes, it will. Usually, again, where my modes, the easiest way to see how my multi-mode structure of the field shows up is to think about modes, for example, laser cavity modes. And think about those laser cavity modes as modes with randomly distributed amplitudes and uniformly distributed phase, which is usually standard way of thinking about those modes. Now, the statistics of those modes will be Gaussian. It will be exactly these statistics here. These statistics here, generally right distribution, and then depending on whether it's A equal to 0, it will be a Rayleigh distribution or Gaussian distribution. This is the easiest point to connect. But now the second part of your question is very deep. So you're already thinking in terms of a different model. What I suggest is that I already have this randomly distributed amplitudes. And by the way, the way my Gaussian distribution shows up, my Gaussian noise shows up, is through the Fokker-Planck equation. The Fokker-Planck equation, where phi, it will be with the Fokker-Planck equation, where the number of modes will play the role of time. How about this? So it will be the Fokker number of modes, right? So you're asking about the number of modes, how number of modes shows up. It shows up in the same way as time shows up in the evolution of the heat diffusion type process. So through the Fokker-Planck equation.
I have more and more modes.
Yes, you have more and more modes and becomes more and more Gaussian. I mean, you can calculate all the moments, and you will see how those moments, if you have just few modes, then it's not Gaussian. Then you have some harmonic polynomials, whatever. But then if you have more and more modes, they become indistinguishable from Gaussian if you're looking at high order statistics. Now, but my idea is that, in fact, I don't know how to answer your question with Langevin noise. But of course, I'm bringing up this Fokker-Planck equation argument because this would be my idea of how I could try to answer your second part of the question, which still I don't know an answer to.
Good, thank you.
Alma,
Very beautiful talk.
thank you.
My question is regarding temperature contributions to damage and all that stuff. It's not considered here, right?
Not here, not yet, Alma.
And do you have like some experiments where you have tested like how good?
We had a lot of damage over my lifetime. There were a lot of black swans. I can.
That I know, but I'm
I-
talking about the statistics that you are like
Statistics.
projecting, right? Like how long do I, or how many pulses do I need to damage this and then that this? Have you tested that experimentally?
Not exactly damage, because again, the criteria of damage is a difficult thing, right? Sometimes, I mean, even 30 years ago, you're coming to some really high-profile lab, and some people are doing attosecond science, maybe not 30 years ago, but something really that brings a lot of publications. And then there will be somebody who is working on laser damage. And this person usually he wants to retire, and or they want to retire immediately, because it is so difficult to come up with an experimental criterion how to judge the damage. How do you, I mean, this criteria. But of course, we had a lot of measurements on statistics with respect to how this noise show up in experiments, right? So if you have supercontinuum spectrum, supercontinuum experiment, in a fiber, in a hollow core fiber, and in a hollow core fiber, you have always ionization. Now, above the threshold of ionization, as you're starting ionizing your gas inside. So this is a hollow core fiber once again. And inside hollow core, you can ionize the gas. As you're approaching this, so it's simply from 21 microjoule to 23 microjoules. And then here, you see how the noise builds up dramatically. So from these statistics, we can derive, anyone can derive those results.
Thank you for this insightful talk. I wonder if the next level of sophistication can be to include damage, which is not simply dependent on the parameter of a particular pulse, but cumulative damage that depends on the history of exposure, because that's my feeling is often the case.
Yeah.
You can probably add something like that into this model.
Well, to be honest, here we still don't have to have even a single pulse damage model. We're still not there. We're still at the stage where we're analyzing where we have this risk, where we're above the threshold for the damage to happen, to come later. But then for the damage, of course, you have to include multiphoton ionization or tunneling ionization plus avalanche ionization inevitably. And this is where already things become difficult. But then again, prehistory would be yet another. So we're still a couple of steps even before that stage where this prehistory can be included. But you're right, yeah, prehistory is important.
For those like fragmentation process, but
Mhm.
when it goes developing to multi-filament, would the beams still be like mutually coherent?
Usually not. It's not again, the picture of this multiple filamentation is completely analogous to what we have in solitons in time domain. So, but in the time domain, we have this picture when solitons, this is more or less the standard textbook picture of breathing soliton dynamics. So the solitons, as you include only instantaneous nonlinearity and second order dispersion, the solitons, they tend to form this bound state. And then they exist as breathers and they absorb experimentally. But this is not possible. Usually this is not what's happening in the space domain. The equations are the same. But because of the ionization makes equations different. And because ionization is an important, I mean, you always have ionization here. Then those solitons, that used to be the same beam, they become independent. So they don't know about the existence of the other soliton. So the beam becomes incoherent. I mean, you can observe some limited interference between filaments. This is being done. So I'm not saying they're completely incoherent, but it's completely disconnected. So this soliton, you cannot get back those solitons, those filaments back together again. For solitons, they're getting back together more or less as a part of this breathing dynamics, this cyclic periodic breathing dynamics. There's not happening to filaments because ionization makes it stochastic.
Let's thank our speaker again.